okay, which we term it as segmentation. Okay, right. So when we write an assembly program, right, or so suppose I say I want to write A equal to B plus C, darker color, oh so bad, okay, fine, okay, I say int ABC A equal to B plus C, okay. Now please understand that when this program gets compiled, right, the compiler does not know where A, B and C would be loaded in the memory, right, but it needs to know because A, B and C are allocated space in the memory, and whenever you are trying to access that, it should be accessed from the memory wherever it is mapped to, and then you read the value of B and C, add it, and then you write the value into the location A. So let me say that A is stored at location A, B at say location capital B and C is at location capital C. So the x86 code for this would be move say some EC, so EDX comma value of B, move ECX the value of C, add EDX comma ECX, move into location A the value of EDX. So the value of small b will be loaded into ETX here, the value of C will be loaded into ECX here, both will be added, the answer will be in EDX and that answer will be stored back into location A, right. Now this is what the compiler has to compile, followed. Now when the compiler wants to compile, will it know where A, B and C are? It will not know where A, B and C are, correct. So it needs to know what A, B, C, but it cannot. So arbitrarily it will say that A is stored at this is equal to 0, what will be this equal to? 4, because integer can be 4 bytes, so 0, 1, 2, 3, so it will make 4 and this will make this as 8, okay. So it assumes that your data segment, so when I write a program there are two segments, one is your code segment which carries all your instructions, there is a data segment which carries all your data, okay. Now the compiler assumes that your data segment starts at 0, means it starts at logical 0. So the logical address of your data segment at the time of compilation okay. Now this is your RAM, okay. So there will be, when this program gets executed, there will be a code segment which will contain all these 4 instructions. Let us assume each instruction is 4 bytes. So let me say there are 6, so let me say there is one halt at the end. So let me say there are, so 4 into 520 bytes. So it will be loaded from 2000 to 2090, okay. This is where your code will get loaded. As far as this first level of lecturing is concerned, first level of understanding is concerned, let us assume that the data will be loaded between 2020 to 2021, 2023, 2024, 20, 21, 22, 23 will be A, 24, 25, 26, 27 will be B till 2031. 28, 29, 30, 31 will be C. So your data is loaded at this, Okay. So your code is loaded at 2000, your data is loaded at 2020. Okay. Now there can be another instance where another time when you are executing the program, assume we are now executing it on a server, let it be some program related to your Gmail. Next time when it is executed, so somewhere some 4000 to 4019 it will be loaded, your code I will call it CS now, code segment. CS stands for code segment, and your data will be loaded somewhere between say 1015 and some 1035 or 12, right, 1026. This is where your data will be. So where is A loaded here? A is loaded at 1015, 1016, 17, 1019, 1023. In the previous instance where A was loaded at 2020, B 2024, C 2028. Okay. So, but irrespective of wherever I load the code segment and data segment, this program should work correctly, and I should have compiled only once. I compile only once. The same a.out, I am executing it once. At that point it can get loaded into 2000 to this. At another point it can get loaded into, whenever I am executing next time, it can load into some other memory. You can execute the same executable on different machine. Like for example, one of our word processors compiled only once by Microsoft, right? Now it is going to get executed on different system at different points of time. So it can be loaded anywhere. So this type of a compilation, one of the things the compiler wants is what we call as position independent compilation. I need to compile in such a way that I am not bothered about, I should not care about where the program will be loaded, where your data will be loaded. That is very, very important. Able to follow? Right? So this comes, this basically now comes as manifest in the form of what we call as segmentation. Many of the operating systems, even the modern operating systems, do not exploit the segmentation that is present in the Intel architecture, right. I for sure believe that today we are talking about security. One point of time, if at all there could be a secure system, then it will be Intel based, because they have the foundations for building in security. Okay, that is why I am teaching you well in advance. Okay, someday when you want to talk about security, certainly Intel will, the amount of hardware thought process that has gone into building both inter and intra process security, as I mentioned in the first lab class, is phenomenal in Intel. So that is why I am taking that as a case study, so that you could understand that in a better, understand and appreciate some of these concepts. Okay. Now we introduce this segmentation. Unfortunately, none of the operating systems. So next time when you do the operating system course, you will be learning something called XV6. Okay. So last few years we have moved on to what we call as XV6. Okay. XV6 is a abridged version of Linux. Linux in 8000 lines. Okay. Linux runs to millions of lines, close to a million lines. Okay. They are even the major part of Linux. But we have MIT has taken a lot of effort to bring it to some around 8000, actually literally 8050 lines, including comments, spaces, brackets, everything. It is a C code. Okay. Now in that framework, so we will do a complete deep dive of that framework, so that you understand how an operating system like Linux could be built. I think that is very important. So we should go to that level. That is why we are spending lot more time, and that XV6 is bootable on an Intel platform. Because of all the architectures today, Intel is the most open architecture. You see 3,000-4,000 pages of manuals, right? Already you see, right? So Intel has the most well defined documentation, etc. So lot of education materials have gone around Intel and AMD processors, namely the x86 processor. So we teach this because for you to understand the first few classes or even the first few assignments that you will do in operating system, which is extremely crucial, this knowledge of x86 will take you really far. So when you want to understand the bootstrap, the real booting up of the operating system, the xv6 that we are going to see. Now, so what is segmentation? So if you look at the Intel architecture, there are 6 registers: CS, DS, ES, FS, GS, okay, where CS actually stores the base address. Actually from CS I can get the base address of the code segment. From DS I will get the base address of the data segment. ES, FS, GS are extra segments, and of course there is one SS which will give you the base address of the stack segment. Okay. Now what we do is, whenever I access memory, automatically your DS will, the address that is stored in DS will automatically get added to your address. For example, now I would have put here 0, I would have put here, I would have put here 4, I would have put here 4, I would have put here what, 8, and here 0 while compilation. When I load the program, before loading the program, the operating system will allocate some space for you in the memory, correct. One of the important thing is the operating system has to allocate some space. I say I need some space for executing code, keeping my code and keeping my data. The operating system will allocate some space. What do you mean by that space allocation? Essentially it will create some segment for you. What it means to create a segment, I will talk about it, and it will give you a base address for the segment. That base address, it will store it in your corresponding segment register. So your DS here will store what, 2020, right. So when DS stores 2020, then what will happen, whenever I am accessing memory, automatically DS will get added to it. So now where is A stored, where is B stored, 2024. So whenever I am executing move edx comma 4, the moment it sees the bracket, it sees 4, it takes the base address of the data segment, adds it, so automatically this will be routed to 2024. Similarly this will be routed to 2028, this will be routed to 2020, okay. Next time when the program gets loaded here, your CS, your DS will become 1015. When DS becomes 1015, this will get routed to 1019, this will get routed to 1023, okay, while this will get routed to 1015, whatever, okay, and that is what you see here, right, 1015, 1019, 1000. Segment is larger than the largest contiguous memory, we will address that. So there are a lot of solutions for this, that is entirely the segmentation. So we will answer that question, this answer to this question needs 2 months for me. When the system basically, when the program actually gets loaded, the executable file will tell the operating system so much byte is needed for code segment, so much byte is needed for data segment, correct. So this fellow will allocate that. So the operating system will know while it is going to load a you press a dot out enter, immediately the operating system will go and analyze the a dot out, and the first thing it will find out is what would be the size of the code segment, what should be the size of the data segment, and it will allocate. Only one answer I can give you immediately, like, so I have only one, so the answer for this, I think maybe you have already understood this, I have only one data segment, why should I have all these extra segments, ES, FS, GS? I have only one data segment is there, and you say everything will be inside that data segment.
You have
large files, ah? Now I am executing a program, file will be in the disk, so why as a memory I am not bothered about file size, right?
to store dynamically.
So when I do dynamic allocation malloc, that I will not know, right? As a compiler will I know? No. So what will I do when there is a malloc? What will I do? You just allocate a space for the pointer, correct? Followed? That pointer, there will be a pointer to the memory that starts, and then the remaining entire memory can be taken out by another data structure called a heap. Okay. So what happens is, in your code, when the code is actually getting executed at this point, when there is a malloc, you mean the malloc is actually a system call. It is called a system call. System call means malloc, I am a program executing malloc, I cannot go and allocate memory for myself. I go to the operating system God and say, hey God bless me, give me some memory, right. So what is our argument to malloc? Size. So much memory I need, correct. So the operating system will bless you, Baba, take it. From where did it bless you? Somewhere here. So this is your extra memory, correct. So when you do the operating system course, you learn lot more about this. There is all the free memory will be kept in a heap, right, in a heap. Why heap? Because I want some memory, right, I need to find out the memory closest to it, correct, closest in size to it. I could have best fit, worst fit, different algorithms are there. Every time I ask, I want 1000 byte of memory, right, I will go and find out that closest contiguous memory which is very closest to 1000, it is just greater than 1000. To do this type of a searching, yeah, max heap or a min heap will help. So the heap will basically store the values of how much free memory is there and where, and so you can search the heap to find out something which is very closest to you. So if you start querying for 1000, the element you will land up will be very close to 1000 in the heap, okay. So that is why heap type of structure is maintained, basically where free list will be there and you can take. There are also algorithms like best fit, take the largest chunk of memory and keep filling it. There is another algorithm called worst fit, take the smallest chunk and fill it. If I want to implement the best fit and the worst fit, then I can use a max heap and a min heap, right. So the moment I do a malloc, I will basically get some extra memory from the heap, and that memory, say it is at 10,000. Now I will make ES is equal to 10,000, and every time I will access this data, I can say, if I just say moves 4 comma EX, automatically DS will be added. But I can also say move ES colon 4 comma EX, then I will go and access the 4th byte in your segment pointed to by ES, correct. You are getting this segment pointed to by ES, I can go and get it, okay. So that is why extra segments are used. In case I want more memory than what I see, when during a compilation, if I have a malloc statement inside a compiled program, the compiler in no way can find out how much memory you need, because it is dynamic memory allocation by name. So only at the time of execution you will find out how much memory extra I need, and then I can use these segments for doing this. So that is why extra segments are currently being used. Fine, okay. Now I will come to doubt. Yeah.
So does a heap affects the performance, like using heap memory?
There is no other go. Heap actually improves the performance. Somewhere I should go and find out where the memory is. Heap can do it in logarithmic time. The other solution other than heap would be a linked list, linear list.
No, I am saying compared to DS, storing any information in DS or storing any information in heap, does it affect the performance?
Well, why should it? No, I didn't get your question. Can you repeat it? Can you repeat the question?
Suppose I am writing a code and I did malloc say 10,000 space.
Okay. Oh, if I access through ES and I access through DS, is there a difference?
Yeah.
No, there will be no difference. Both are segment register, it's in the proximity of the. So accessing any memory, there will be no difference.
So like we don't have, there might be multiple malloc. So like the number of mallocs, there could be multiple number of malloc statements, right? So there could be multiple data.
Yeah. There
So
could
how
be.
can- like why only 3 registers? We might be more-
Yeah, that's a very interesting question. So why only 3? So let us go to, I'll be teaching in the morning course in the theory part. There will be so many variables, right? 1000 variables, correct? Now I have only 4 general purpose registers. I will be very happy if I store the variables in the general purpose register, correct? Why I should be happy? Because I have very fast access. Right?
So no, like
Wait. Why 4 registers?
All the variables and all we already know at compile time, so that time there only 4 registers will suffice there. But now we don't know how many.
So your malloc, number of mallocs in any normal program, you can kill the program. You can kill any architecture by writing a program that is anti-architecture. Okay, meaning for every architecture you can, for every policy that I am going to tell here, you will always have a program that will kill it. So that is easy possible. But in an average, when you write a program for sake of writing a program, not for killing the architecture, then those programs, if I say just 4 registers are sufficient to handle variables, can't 3 segments enough for handling mallocs?
No, say if I have a malloc statement in a while loop where say I'm
You will not have a malloc statement.
No,
You will
I'm
actually free it.
like what I'm trying to say is there might be more than say 100 non-contiguous data segments to the program, right? So how will we know where the data segment?
Yeah. So first thing is you will not have such things. Suppose you have, then you have something called a descriptor table. We are going to come to those things, where you will maintain the information, but you will vary the registers of this. Okay, if I start answering that question, everybody will go for a toss. But your question essentially will get handled. But the reason for why 3, the answer is 3 empirically, meaning analyzing all the workbenches. Workbench means typical programs that will run on a system. 3 is more than enough. Correct? So that's sort of at any point of time. Okay, that's why people fixed 3. What happens if it is more than 3? Right? You have 4 general purpose registers, the remaining thing your ESP and all will be used for stack, etc. EBP for base pointer, etc. There will be 4 general purpose registers for sure. Okay, available to you. ECX will be used for some counter. If you have a while loop, that's all, ECX will go there. Okay, so there will be some 4 ESI, EDI and EAX, EBX. And EAX will be used lot of time. If you use a div, 2 of those 4 also go off. Okay, so still we are very happy. Intel survived for 3 decades using 8 general purpose registers. So why? Okay, again that's an empirical analysis. We will come to that, right? So all these why are very important question. Why 3? Why not 4? Why not 2? All these are very, very important questions. For several things in architecture, this why has been evaluated on some benchmark, and so there will be a paper on why 8. Okay, so lot of the time why is the answer is as why you didn't attend morning 8 o'clock class, right? Okay, 2 days you will say feels I slept sir, then the third time you will say you have to find some random reason. So whatever occurred to your mind that day you will tell that as a reason. I can't verify that anyway, nor am I interested. I want to ask you a question just to bully you, where you right? So similarly here that day when that designer tried to design this hardware, he was very happy doing 8, he was very happy doing 16. Normally it is power of 2 because that many bit you need to address them, then if it is n 2 power k then I need k bits. If I put some prime number then lot of bits get wasted there. Okay, so normally it will be power of 2, that's one decision. Many times it is the best I could do at that point of time, or my mood, I had that mood that day I decided 8. Okay, this is as random as this. Okay, so lot of answers in organization are like that. Okay, but we will see many things, right? Because when you look at later things like there was a very nice paper, some decisions, some statements made say 2 centuries before, or sorry 2 decades before, how are they relevant today? Like there was a very nice article in Spectrum. I'll try and download it. Probably the last class of computer organization, I'll give you that Gyan and go. Okay, so that will be very interesting. Okay, so fair enough. So I have answered, it's an elaborate answer for your question. So, yes.
Can the values in the segment register be manipulated by us?
So yeah, now comes the other questions. Segment register, who will manipulate, how it will be getting manipulated, will come all those questions I am going to answer. Chal, you understood what is segmentation. So segmentation, see segmentation, the first interest of segmentation was driven by the compiler, which said that at the time of compiling I don't know where the data is going to be loaded. I want to assume it is 0, and the hardware please support me, so that operating system and hardware please support me so that I can do. So what is the role of operating system? Operating system will allocate a segment and it will initialize the segment register. What is the role of hardware? Whenever there is a memory access, the hardware will take that value from the address, like 4 here, value of the address from the instruction, add it to the segment base and fetch that. So please understand, the problem of the compiler is being solved collectively by the operating system and the hardware. Okay, are you all getting this? So this is one very interesting thing about segmentation.